So we have now two speakers left, I think. So we have Asaf, at least last time that I was checked, he was there, but I don't see him anymore. So there's only you left, Anubhav, among the speakers. So for the discussion here, I wanted to maybe bring two things. One was actually is coming from the discussion that we had with our experimental colleagues. So they would be happy to see some success stories about using machine learning to predict something, or and so far most of the examples that we have seen are essentially to speed up the DFT calculation, and in a sense MatBench mainly also goes in that direction, though. I mean, you showed that there are some of the databases were experimental ones, but usually the experimental ones are smaller, so those are those in which we make the biggest error. So I don't know if among the people still here you have an example that we can show to our experimental colleagues where really using machine learning was a breakthrough or something really very helpful to you know, to give success to one of the projects. So apart from speeding DFT, that's essentially the main application that you all see for I mean, I think that, you know, the example that Yusung was showing where we can go in the direction of these generative adversarial network, for instance, could be a way to get success. I mean, we have seen from IS that, first of all, it's not very easy. And from the example that he gave, he only had something like the stability, and it was not a full success. So maybe the amount of data that we have is not yet sufficient to go to something like that. So.
I may come back to you on this in a year or so. So we just finished a screening project where we were looking for new channel materials for oxides in transistor channels, and we're currently trying to create these materials, create actually transistors out of them, and test whether this happens. And these materials are actually being predicted after DFT calculations, training machine learning, and then developing new candidates. But now we have to do the actual experiment, and that is tough work.
No other examples? Okay, so then maybe I can bring my second point, which was about the representation. So we have seen that, I mean, the way in which you present the structure, and also in the case of MatBench, this is something that you didn't highlight, Anubhav. So you showed that the different methods have, you know, you presented them in terms of the classical random forest and so on. Then the neural networks with the convolutional graph networks. But there's also the way in which you represent the data that is important, and especially, I mean, when I think about again this these generative networks, what we want in the end is that to predict a structure or a composition. And so, what is the best way to represent that? Did we already achieve some kind of agreement about that? So yesterday we were discussing about SOAP and then ACE. Sorry, is there other ways to represent things that are found to be more appropriate than others? Yes, Anubhav.
So regarding the topic of descriptors and representation, you know, what seems to me to be happening is that as you have more data points, the less important it is that you upfront come up with a good descriptor, because the layers of the neural network will learn your descriptors for you. And so, you know, I'm not sure that we've come up with the best descriptor, but as the data sets get longer or get larger, it might become less and less important for us to come up with the best descriptors.
It depends it depends for what, Anubhav, because precisely, I mean, with you know, with Automat Miner, we have a huge amount of features, and so you're perfectly right with respect to that. But now let's say that you want to optimize. There was the, you know, in the talk of Yusung, he was presenting this global optimization or the generative adversarial network, where what you want to do is to achieve one specific property. What is the structure that you need to create? And since, I mean, what we would do in the case when we use the Automat Miner, we would be able to say, oh, if a material had these features, then it would have this property. But we aren't able to say which material has this feature. So this is why I'm asking the question.
Yeah, I mean, for that, you know, this is still a tough problem. I've seen people have a second model, right, that takes the descriptors and tries to turn them back into a crystal structure, right? So you end up with two models that end up needing to be used. But yeah, it's still an open problem as far as I know, right?
Someone else wants to comment on that?
Well, so in my case, I just only use the composition as a descriptor because I want to search for a certain composition.
But so how did you represent the composition?
Oh, my composition is just a weighted average of the weighted composition vector. That's
so you have a vector
else.
with the
I just have like 12
elements,
and my first number is the amount of element 1, and the second vector of the second entry is the amount of element 2. That's just.
But then you have to do this, what was called a global optimization in that case. So that means that you have to search that, I don't know how many elements you consider.
Yeah, so I mean, I didn't talk about this, but it could have been in this session as well, right? So basically I have a 12-dimensional element space. So we did a pre-selection on the elements, and I calculated the properties, 5 properties effectively that I'm interested in, for all the primary and binary oxides. So I take 1 element oxides and 2 element oxides. So three elements, right? So 2 elements and oxygen. And that basically I developed until a database of 4,000 materials, amorphous materials, which I then use to generate models that predict properties of arbitrary complexity. And then I use minimize an objective function that tries to kind of improve, or let's say define the optimal candidate for all my properties at the same time, because I don't just want to tune the band gap or something. I need to kind of have 5 properties in the right range at the same time.
Yeah.
So yeah, I think in the case of inverse design, the feature choice will be much more important than in the direct problem, where it's of course much less important, because if you have more data, then it doesn't really matter. But in the reverse, when you do generative modeling, I think that case is very tricky, and I don't know. I mean, I think it's still somehow an open question to see how we could.
Yeah, I mean, in the video that I was showing, where, you know, with the faces, you know, if we were able to find this latent space in which we can say, okay, I'd like this material to be more conducting or more transparent or whatever, then it would be I mean, super cool, I think. But indeed, it's still a very open and difficult problem.
You have seen some examples in the first talk, but they were quite.
But it was
limited.
about stability mainly, and so we could see really two things, and so I mean,
limited in composition.
But you know, when you have the faces, people, I mean, I showed the example of the women men thing, but they have something about also different kind of thing. They can make the people younger, older. They can make their change the color of the eyes, the color of their hairs. So they found in this space of the faces, they found very many direction, and so it would be interesting to have something like that for materials as well.
And also the big limitation, I think, in my opinion, will be the amount of data we have with respect to what they have for faces in our material space, which is more limited.
Yeah.
Well, I've also seen that some properties are much easier than other properties. Stability, in my case, oxides, almost, I mean, with very easy to model that correctly. Other properties, things that effectively measure electronical conductivity of an amorphous material is way harder to model properly, and you have much more noise, and even gaps is also already way more tricky to model properly. So it's a tough problem, and per observable it's differently complex.
Is there any other point that people would like to bring in this discussion about the machine learning, where we should go? So, I mean, there's there's a proposal by Luca for a second workshop. Anubhav. Yeah, I'm just gonna finish my sentence and then I'll leave it to you.
Yeah, why don't you finish it and I'll go after you. Go ahead. Yeah.
Yeah. So, well, Luca is proposing a second workshop in order to find similarity between structure, and this also, in a sense, goes in the direction of the representation of the structures, because to find some similarity, you need to find some representation of the structure and then measure the distance in a sense. Yes, Anubhav, please.
So yeah, just in terms of other topics, one specific problem that we ran into recently in our group is we were just interested in investigating these GANs for materials prediction, and there have been many people that have been publishing crystal structure GANs for doing various things, and many journal articles have been published. But what we wanted to do was to actually say, okay, let's just try running some of these other methods first before we try and invent our own and just see how these things are doing. And what we found is, I don't remember the exact statistics, but let's say there were 5 things published, code was actually available for 2 or 3 of them. The rest of them would say code available on request. And then, you contact
Indeed.
them and they say that the code's not ready. And so, of the 5, we can actually get code for 2 or 3 of them. And then of the 2 or 3 that have the code, only 1 of them is actually installable. And the other 2 or 3 just are broken. And so of the 5 things that are available in the literature, you can actually just try 1 of them. And the other ones are just inaccessible. And so you're kind of forced to it. So I just wanted to put out, is there something that we can do as the leaders of the community or something to try and improve on these statistics and try to make it so that, we can at least try and run 70%, 2/3 of the things that have been published out there and be able to try it. So yeah, if any suggestions would be welcome on that front.
Yeah, I mean, this morning there was Giovanni pointing to the FAIR aspect of the workflow. So sharing the workflow. I mean, what you're suggesting here is sharing the algorithm to do this GANs. I think it's important indeed.
Yeah, and we talked about the DL Hub earlier, which I think could help with some of this stuff. Which if it's on DL Hub, you at least have some file that you can be runnable. But I think it's better in the computer science community in the sense that when people publish things, you can actually run them, and it's more of a requirement. It's not like you can just be like, hey, code available on request, and still be able to publish. So I don't know if people are for being strong, taking a stronger position on this, or whether it's something that we just kind of leave alone, and hopefully the community will sort itself out by having more tools and things to make it easier for people to do this.
Are we done? Okay, thank you very much to everyone, especially to Anubhav for waking up so early.